The satellite is it's a sensor. I mean, it's a spacecraft that has sensors on it. Okay, the light is not that good, but I'll try to see what we can do. So the satellite was launched in about 1997. Oh, it's about 20 years now, maybe 19 years now from now. And it's aimed to measure precipitation in the tropics. So that was the first satellite that carries a weather radar. So the set of sensors in the satellite are a microwave imager, a precipitation radar, and a lightning detector. Let me see if I can. Oh. Sorry. I have an animation here, so I'm just trying to make it work. Nope. This way. This way. Nope. Okay. There was an animation in there, so. So the satellite is able to measure precipitation processes in the tropics. Has basically the latitudinal belt of the tropics, and has data for almost 17 years. The satellite died out 2 years ago and is replaced by now by the GPM. So the first goal of this satellite, of the precipitation radar in this satellite, was to measure precipitation. So just to quantify what is the distribution of rainfall across the tropics. So this is a rainfall climatology from the PR. This is for the two summer seasons in each of the hemispheres. So north, in the top one is the DJF, so summer in the southern hemisphere, and in the bottom is June, July, August in the northern hemisphere. And as you can see, many features, like the classical feature that you get in a climatological class, is you get the ITCC, I mean, a really clear ITCC band, a lot of, let's see if I can move around, a lot of rainfall here in this area, where the ITCC meets elevated topography here, right here, where we are right now. Another one is this that spans from the African West, from the Sahelian plains, and then move across with the flow of the wind, especially with the African easterly jet. And the clear one, the most clear one, is the south, in South Asia. Yes. So the South Asian monsoon, that's the one that everyone talks about, and you can see the pretty clear shift of the rain from almost nothing in summer and to almost everything in summer in the northern hemisphere. So that was the first goal of, that was the kind of the first goal of TRIN. It was measure precipitation. But one of the things that TRIN has. Thank you. So one of the nice things that the TRIN has is this suite of sensors. So it has the first precipitation radar. It's kind of similar to a precipitation radar, a meteorological radar, as the one we have here in Medellin, but it's mounted on the satellite, and it's looking always down, and it's always measuring the very first 20 kilometers. This is about 20 kilometers of where most of the weather phenomena happens. But what is most important of that is that we can get three-dimensional structure. We get volumes of what is the structure of the precipitation systems that falls into the ground. And that was not an envisioned goal of the TRIN, but these characteristics led us to understand much more of what is the convective cloud population in the form that I'm going to show you right now. So, for example, this is so the radar measure, what the radar measure is reflectivity. It's kind of the difference between the radar sends a pulse to the atmosphere, and that pulse source of energy interacts with the particles that are inside of the, I mean, in this case, water particles, or water droplets. And on that, energy returns to the radar, and we can measure the reflectivity, how much it reflects, basically. And the power is proportional to the amount of water, to the size of the particles that are precipitating. That's the reason why it comes. That's the name, basically, of the radar, precipitation radar, because the particle has to be precipitating, or has to be sizable to be precipitating. So it's able to measure not only the size of the particles, so how big they are, but also how many they are. So it's a kind of an indirect measure of how much is precipitating. And this is an image, an overplot image on the back. So this is Colombia. I think you can recognize here Panama. Here is the Guajira. It's an overpass of one of those measures that the satellite did. On the bottom is just a visual. It's like a photograph from GOES of the clouds, the cloud shield that has happened in there. And you can see the colors. So yellow and these darker colors are more intense precipitation, related with more intense precipitation. And these lighter colors, the green and the yellow one, the green and the white ones are lighter precipitation, so few precipitation. So that was the first thing. But what is nice from this radar, or from any radar, is that you can make a cross section on the volume that you measure, and then you can see inside what is going on inside of the cloud structure, and you can go a little bit further in this. And you can kind of identify parts of types of the cloud structure that is inside of what is precipitating to the ground. And in this case, this is a kind of a classical example of what a difference between a convective and a stratiform rain means. Convective rain is characterized. This is vertical. This is just it's a kind of a cross section here. So convective precipitation is basically driven by low level convergence, strong updrafts. So the air is moving from the lower levels to the upper levels of the atmosphere. If there is a lot of humidity in the air, that air is going to cool down, it's going to condense, and it's going to start moving upward, and it's going to start condensing, forming particles, and precipitating. So that's what you will see in a classic convective shower. That will be the vertical structure of the convective shower. But then the convection kind of die out. I mean, the energies get depleted. There is less low-level convergence. There's another process of entrainment and flows of air that are coming into the system, and then the kind of the convective towers collapses. I mean, sometimes collapses, sometimes it's formed by another processes, and then you get like an extension of broad rainfall that is not so tall and that is lighter on the ground. So basically, the analogy is that these elements are those intense and really convective showers that we get, and these are the lighter precipitation that comes after those intense ones. So what with TRIM, the nice thing with TRIM is that we can identify those types of convective structures in the data. So we apply a methodology to identify the most pronounced convective elements. We separate those two elements within the data. We've found extreme events, so those that have a higher reflectivity, so it means that has higher particle contents on the atmosphere, and we categorize by how tall they get, so if they get really tall in the atmosphere, and we call them deep convective cores, and how broad they get, so we can call them wide convective cores. There's another component that is the broad stratiform region, that those are stratiform volumes that gets really extends in the horizontal extension. And the last one is we can also find those shallow convective elements that that one of the reflectivity pixel never reach up or from the 0 degree. So we can identify kind of a part of within that within that storm. What is the advantage of doing this? Is that we can associate each of these convective echoes to fundamental elements belonging to the cloud population. And these 4 ties that I just talked about, it turns out that they correspond really well to the life cycle of what we call a really organized mesoscale convective system that is kind of an organization of many storms. So the deep convective cores usually are associated with the early stages in the life cycle of the mesoscale systems. The wide convective cores are mature stages, so they are not that tall. They are aggregated. They tend to coincide with the most rainfall, with the broader rainfall. And later, when the ambil forms, when there is a lot of spread of particles onto the nearby atmosphere, a broad stratiform or a stratiform rain sets, and then we can associate those as a late stages of the development of this. So we can identify them and then associate them to stages on the cloud population. Just as a quick example, this is a different radar. This is the radar located here in Medellin, and this is how they look. How one of those, and in this case, the 3 elements. This is just a kind of a case example of what a deep convective core may look. They reach really high, up to 15 kilometers from the atmosphere, and they're really, they're really svelte. So they are really kind of really erect, what we call. So they are really narrow in area, but really deep they can reach it deeper on the atmosphere. So this kind of be the wide convective cores, or those are rainfall that are spread in the mesoscale, and later, this one will be a more broader areas of a stratiform region that is really composed by light precipitation. So let me show you where do they occur. So we have 15 years of data, almost 17 years of data, and I'm going to show you where do they occur for these 3 months of the year. So let's talk about the first two ones, the shallow ones and the deep ones. There are 2 elements that are really opposed in nature because they occur in different places of the world. The majority of the shallow convective cores occur in the ocean, and almost all of really deep elements occur over land. So the reason for this is kind of a phenomenological reason. The ocean has more salt, bigger particles, and less concentration of aerosol. That provides the cloud condensation nuclei to easily become a shallow isolated core. While the deep convective cores, they are favored by, they kind of sits near mountainous regions, but also they get most of the energy from a thermodynamic difference between the thermodynamic profile of our land and our ocean. That the thermodynamic profile over land is steeper, so it means that there is more buoyancy available for these elements to become more easily to form over land. Now there is these 2 other ones that they are really closely related because kind of they are subsequent elements of one of each other. Those are the wide convective cores that are kind of what the classical definition of a mesoscale convective system is: a well-formed system, organized set of storms that have reached the mesoscale, so they have extended really broad in the atmosphere, and they kind of locate mostly over land, but they also extend a little bit further from the ocean. Further to the ocean, to the nearby ocean. And the broad stratiform regions are those big regions, those stratiform regions that mostly form over the ocean. So you see that they are kind of the extension of what a wide convective core might be. And in especially particular regions of the world, they are influenced by the local convergence of energy and distribution of winds. I'm showing here June, July, the climatology of the wind vectors and divergence. So if you get these kind of colors, you will get convergence, low-level convergence. We are here in the surface. And you can associate the maximums of those systems, of those mesoscale systems, with well-known phenomena, atmospheric phenomena that happens over the tropics. The ITCC, I mean, the confluence of the trade winds in the ITCC that sets and helps the formation of these broad stratiform regions. The convolution of these two jets, or these two low-level or interaction in these two low-level humid air masses here in the coast of Colombia and Panama, that sets this maximum here across the same region. Or the Africa, as I was telling you before, the interaction between these jets, the African easterly jet that forms because the difference in temperature between the big Sahara desert and the moist surrounding, and forms some waves that interacts with the low-level entrance of winds and provide the moisture necessary to, provide this meteorological or this climatological maximum in mesoscale convective systems. And the later one will be the monsoon. The classical pile up of energy here in the coast of Burma and India that makes, that brings all this rainfall through the year, or especially in June, July, August, of course. So just moving a little bit, I think I have 2 minutes. Yeah. So I'm just going to show you one important implication of these systems. We want to understand what is the contribution of those elements that we find, we routinely can find in the data, and how they contribute to the climatological range. So the question is, what percentage of the precipitation is produced by these extreme events? So I'm going to show you the example here in South America. This is the rain rate average for June, July, August. And this is kind of the scale percentage of the rainfall that is produced in this area from one of those systems or elements. What is interesting is that here in the coast of the Pacific coast of Colombia, almost 50% of the rain comes from these wide convective or mesoscale convective systems. And if you sum up or add up all these systems, you get up to the 70% of the elements. But what is more interesting is that you still get a lot of rainfall here in the Amazon, but you don't get too much contribution from those from the extreme convective categories. And what is going on in here, and what is important, is that the convective categories, the convective elements that are produced here in the Amazon, are not as extreme as they are in other regions of the world. And if you kind of make a guess comparison, you can see that the values of the ones here in the Amazons are more or less related or compared to the ones here over the ocean. So we can conclude that the convective element that happens in the Amazon are kind of or the Amazon behaves like an ocean, like a green ocean that produce convective elements characteristic of a oceanic environment. Let me finalize here. I will just leave with my conclusions. I can think I said a little bit too much, and if I will take any questions if he wants.
So, again, really wonderful talk. And it's really, first of all, I love that paper. It's one of the, I think, the paper that really trying to link the phenomena to the processes behind it. Mm-hmm. And we actually use that a lot when we are explaining our observational result. So it's really interesting you point out the difference between the convection on the west side of Andes in Colombia mm-hmm. area versus inland Amazon. Mm-hmm. And
this kind of
yeah, and so on the west side of Andes, is it more? So that's more. Is it? How does topography on the east side of Andes? Wait, west side of Andes, like
so this side.
No, on the other side.
Oh, here.
Is that because of a charcoal jet? Or
Yeah,
I'm
it's
not
kind of a, I
familiar
mean,
with that.
this is the Andes standing here as a topographical barrier.
Okay.
So what is going on in here is that the confluence of the Choco jet, and there's also a recurving of the Intra-America's low-level jet that is
Okay.
bringing moisture and then just kind of a converging in there and just setting the favorable environment for a deep or one of these big systems to happen in there.
Okay, so there the convection is more like a convection over land, right? Organized 50% of rainfall coming from more organized.
Yeah, in fact, it's one of the places in the world. If I am going back to one of these, this is one of the few places in the world that you get, wide convective cores over ocean. So mesoscale convective system, well-organized mesoscale convective systems over the ocean. And you might not find this, you will find this in the Bay of Bengal. I mean, so the convection is as strong, maybe, as the monsoon, basically. That's what is happening there.
Do they propagating from land to ocean or vice
versa? They kind of form, there is a small, ridge nearby to the coast, and they kind of form in there and they propagate. There is a famous paper of Mapes, 1993, that talks about that easterly propagation of those systems that is basically associated with a gravity wave forming on the topography and then moving offshore.
Okay, thanks.